Okay, today's topic is utility functions for the tree, which is a recursive type. Let's see what we have. First, let's write one function called depth, and that will compute the depth of a tree. And we are talking about a generic tree, can be binary, can be ternary, or whatever. So here we have a figure which shows a tree, and we see that it can have a subtree 1, subtree 2, and so on till subtree n. Now, given these subtrees in the tree, we want to compute what is the depth of the whole tree. Then we can think in this way. Say if d1 is the depth of subtree 1 and d2 is the depth of subtree 2 and so on, dn is the depth of subtree n. So say by some magic we have those information d1, d2, dn. Then the formula for calculating the total depth of this whole tree will be getting the maximum of those d1, d2, dn, right? That means whatever is the maximum height, and then plus 1 because of this black node, right? So that will be the formula if we have this d1, d2, dn information. And in recursion, you know that by recursion magic we can assume that we have those d1, d2, dn information for the subtrees, right? And then we can just use this formula. Now recursion also needs one base case, and here the base case of a tree can be just one node, which is a leaf node, right? And then the tree depth is just 1. So that means the function depth may look like this. When depth has input which is just a leaf, doesn't matter what value is there in the leaf, the depth is going to be 1. And in other cases, when the tree has subtrees and that subtree array is C, then we can compute the depth of each tree in the subtree array. And how we do that? We use map and apply that same function depth on each item. That is how map works, right? Map applies the function which is the first parameter of the map on each item of the array, which is the second parameter of the map. And that is nothing but what we saw before, that d1, d2, dn, right? And then we get the maximum of those maximum depth of those subtrees, and then we are going to add 1 with that to get the final depth, right? Okay, so in this figure, the say if the input to this depth function is just this node, that means it's a leaf node, then the depth will be 1. If the input to this depth function is this whole tree, then the depth will be first calculating the subtree depth, which is 1, right? And then this subtree depth here is actually 2, and then maximum of this subtree depth will be 2, and then we are going to add 1 with that, and that 1 stands for this node, right? And then the final answer, the depth of this whole tree will be 1, 2, 3. Okay. Now let's talk about writing another utility function, which is numLibs, which calculates the total number of leaves present in the tree. And when the tree has just one leaf, then the numLibs is just 1, right? Because there is only one node. When the tree has subtrees, then we are going to apply the same function numLibs on each item in the subtree array, and then we can just sum them up, those subtree arrays number of leaves together, to get the total number of leaves, right? So in this case, if we pass this whole tree as the parameter to this numLibs, then the first subtree is this part, right? Their number of leaves is 1. The second subtree is this part. There the number of leaves are 2, right? So then here we are going to sum them up, so 1 and 2 together, and then the total answer will be 3, the number of leaves. Now in some other application, it may be important to include not only the leaves in the tree, but also the inner nodes. So inner nodes can have some values in some application, and in that case the tree type we can define as similar before, just one extra thing we need to add, which is 1a, and that can stands for whatever type and value the inner node has. Right, so it's very similar to what we had before, only one extra a here, which stands for the inner node's value. Okay, now let's see how the depth function for this newly defined tree data structure, newly defined tree type will look like. Fortunately, it looks very similar than before. So depth of leaf is 1, and depth of a full-fledged tree is whatever is the maximum depth of any subtree plus 1. It's basically exactly same logic as before. Now let's see how we can write the number of nodes, that function in this newly defined tree. So number of nodes when the tree has only one leaf is just 1. Other cases, when it has bunch of subtrees, then we want to sum those subtrees number of nodes together and then plus 1 to add what we have in the inner node. All right, to count inner node as 1, we sum 1, we add 1. All right, okay, so it seems it makes sense. Now we can also write another function which computes the total sum of all the values present in the tree. Let's call it in sumVals. When there is only one leaf and leaf value is x, then of course the sumVal is x. When we have bunch of subtrees and the inner node or root node is x, say this is x and this is one subtree and this is another subtree, then we are going to sum up the values, some values of each subtree, and then don't forget to add this root node's value also x, right? So that will give us the sumVals, that function implementation. Okay, we can be also interested in particular for the binary tree, and say in the binary tree the leaf nodes have characters, and the inner nodes have integers. So that's how we want our binary tree. Now to define such type of tree, we can write leaf is char, and then the other option of the tree will look like this, that in the middle there will be an integer, and then on the left there will be a tree, on the right there will be another tree, and we are differentiating this option as binary t as opposed to leaf option, right? So you understand this leaf is a data constructor, binary t is a data constructor, and tree is a type constructor, correct? So the picture shows one example binary tree, and how to implement this. We can write whatever variable we want to assign this tree with. Let's call it tree. And then this tree, if you look at the root node, has a left subtree and a right subtree. So it is of this type, right? It is not a leaf, it is of this type. So that's why we are writing binary t. Then on the left we have leaf x, then we have this inner node 1, which is the root node, and then we have this right side tree, and that is also a binary t with left leaf y, then 2 as the inner node, and leaf z as the right leaf, right? So that can work as the binary tree. And now let's see how much tweaking we have to do on the utility function to work on this binary tree. So numLeaves, number of leaves we want to compute when there is only one leaf, then of course the answer is 1. Otherwise, when there is a left subtree t1 and right subtree t2 and root node is x, then number of leaves is nothing but number of leaves on the left subtree and number of leaves on the right subtree. The root node is not a leaf, so we should not count that, right? Now if we want to write number of nodes, that function, then when leaf is the only node in the tree, number of nodes is 1. Otherwise we have left subtree t1, then root node x, and right subtree t2. Then number of nodes is on the left side we have num nodes t1, then we have one node in the root, and then we have num nodes t2 on the right side. So this arithmetic expression gives us the total number of nodes in the tree. I think that makes sense. Now by class in Haskell, we don't mean an object-oriented class because there is no data involved inside a class. But in Haskell, by class we mean a type which can define what sort of operations can work on which input. As an example, you can add two bools together. So bool is a type, or I should say bool is a class, and we can't add two bools together. So somehow this class information, the class controls what operations can be done. We can't add two bools together, but we can add two nums together. I think that makes sense. And class basically provides some function signatures, and one type is nothing but an instance of a class. Let's take an example. EQ is a class, and it just means that EQ supports equality operation and non-equality operation, whose type is this. All right, so two things are input, and we are going to compare them, and bool is the output of this equal and not equal function, right? So eq is a class where these two operations are allowed. And also we have to remember that class do support inheritance. As an example, num class has subclasses fractional and real. So fractional is num, real is also num. And as an example, we can have an instance of a class. So we already understood eq is a class. So now we want to have an instance of that class eq, and let's call it foo. And what is foo? Foo is a type. We are defining it here using this data keyword. And there are two possibilities for foo. One is it is an int, and we want to call it f int, and or it can be a char, we want to call it gchar. Okay, so that is how foo is. And here we are saying that foo is an instance of eq, and whenever we say that, that means we foo this type has to support these equal and not equal operations which eq class has to support, right? So that means we have to implement this equal and not equal operation in foo class, or I should say in foo type. And that means we have to define this equal and not equal on foo type. And here is the definition. When this foo has int, say one object of foo is fi1, another object is fi2, we call them equal if i1 and i2 are equal. Similarly, if foo is a character c1 or character c2, we call them equal when c1 and c2 are equal. And in any other cases, we call them not equal. That means equal is false. And here is a shortcut way of defining not equal. So one foo object is not equal another foo object if this equality fails, right? That is the shortcut way of defining not equal. So if you look at here, you see that we defined all possibilities of comparing two foo object here, correct? And as we have done that, we can declare that foo is an instance of eq, right? Because eq expects only these two operations to happen, and foo has now supporting those equal and not equal operation, right? So foo is an instance of eq. Okay, now maybe last topic, how to write a function with a generic type. One good example is to write a quicksort function. And how quicksort work? Quicksort takes one list as an input, and also one's particular item in the list works as pivot. Typically the first item of the list we can take as pivot. Then the basic operation of quicksort is, given the list and the pivot, quicksort is going to divide the list in three parts. First part is items which are less than h is the pivot. Then the items which are equal to h, and the last part is items which are greater than h. So that gives us a simple implementation of quicksort. If the input list is empty, then nothing to sort, that can be the output. Otherwise, we can deconstruct the input in head and tail and this head can work as the pivot. So we can extract from tail those elements which are less than h, and they are here, right? And then we can apply quick sort on them as the recursion, correct? And in the middle we have h, and then on the right we have those elements in tail which are greater than equal to h, and we are going to of course apply quick sort on that for the recursion, right? So you can see that it's a very elegant way of writing this powerful function quick sort just in 2 lines in Haskell. Now this implementation assumes that we have a less than operation defined on the list, and also we have greater than equal to operation defined on the list. So we here in this implementation we are assuming that how to compare 2 items that is already defined, right? So and typically that means we are talking about numbers where these operations are defined, but we may want to make it more generic, not only on numbers, we want to also make it work on strings, not only on regular comparison between strings according to dictionary ordering, but also maybe for some application we want to order those strings by their length, right? So what I mean is it will be very powerful to write a sort function called mySort, which accepts a comparison operation from outside as a parameter. The previous one assumes that the comparison is the regular less than and greater than equal. But in this new one, we are talking about accepting a comparison operation from outside as a parameter that can be less than, that can be greater than, or that can be comparing according to the string, I mean according to the length of the strings. And also the list can be integers or list can be strings or whatever, so everything is fluid. How to write such a generic quick sort function? Fortunately it's not that difficult. mySort just can accept a comparison operation from outside, and then the second parameter is the same list. So when the list is empty, nothing to do, we can just output the empty list. Otherwise deconstruct the list in head and tail, and comp operation is coming from outside, how to compare 2 items, right? And then on the left hand side we have a sublist called lesser, and we are going to apply mySort comp again on lesser as the recursion. In the middle we have items which are equal to h, and on the right we have greater, and we are going to apply mySort comp as recursion on greater. Now what is lesser and greater? Here they are defined. Lesser are those items in the tail which compared less. What is the meaning of less? Whatever is the meaning defined in comp. And greater is just opposite, which is not composed with comp, right? So you see that it's very generic, and it can achieve what goal we had here, that whatever is the comparison parameter, I mean comparison operator as parameter coming from outside, that can work on this implementation. Okay, so hopefully it makes sense.